The division algorithm shows the relationship among the terms dividend, divisor, quotient, and remainder. In a standard division problem, a dividend is divided by a divisor to yield a quotient and a remainder. If a particular division has been done correctly, the dividend will be equal to the product of the divisor and quotient plus the remainder. This equation is the division algorithm. With polynomial functions, when a polynomial p of x is divided by a polynomial divisor e of x, the quotient and remainder are q of x and r of x respectively. So in polynomial function form, the division algorithm is p of x equals d of x times q of x plus r of x. The remainder theorem provides a quick method for finding the remainder in those cases where the divisor is the polynomial x minus a. If we set x equal to a, then we can see that p of a equals r. This is the remainder theorem. The factor theorem applies to divisions in which the remainder is 0. In this case, the division algorithm yields. If we now set x equal to a, we can see that p of a equals 0. So the factor theorem states that if p of a equals 0, or in other words, if a is a 0 of p of x, then x minus a is a factor of p of x. The rational zero theorem provides a method for identifying the possible rational zeros of any polynomial function. Take this example. The theorem states that all possible rational zeros will be of the form p over q, where p is a factor of the constant term, in this case 5, and q is a factor of the leading coefficient, in this case 2. So the only possibilities for p are positive or negative 1 and positive or negative 5. And for q, positive or negative 1 and positive or negative 2. Therefore, there are 8 possible rational zeros.
It's important to note that these concepts are connected, and that these concepts are all contributing to the study of equations and the graphs of polynomial functions.
Engineers develop formulae to calculate physical values for naturally occurring phenomena such as temperature, pressure, and water levels. These formulae are often polynomial functions. For example, Environment Canada uses a fifth-order polynomial function to monitor water levels and predict where and when floods may occur. For further examples, we went to Lakewood Systems.
I'm Ken Smelquist from Lakewood Systems. We manufacture data loggers that are used worldwide that are used for monitoring industrial and environmental conditions. We monitor such things as wind speed, direction, temperature, pressure, and water level, and various other parameters. Our data logger actually records voltage only, and the user using it wants it in engineering units. They want it in temperature, degrees centigrade, degrees Fahrenheit, pressure, and PSI or kilopascals. So the units have to be converted from voltage to some form of degrees temperature or PSI. And to do that, we have to do some kind of curve fitting, because the values don't directly relate, and that's where we use the fifth-order polynomial curve fitting. Yeah, we take the sensors into the lab, and since we have known parameters such as water freezes at 0 degrees centigrade and water boils at 100 degrees centigrade, we can actually take our temperature probe and put it at these temperatures, plus other known temperatures by using lab equipment, and gathering enough data so that we can take them back and enter them into the computer, the different voltage levels that we've gathered, and calculate the coefficients for our fifth-order polynomial. Rather than using temperature, what I've done is gone to the field and gathered some water level in meters versus voltage. I've taken at least 5 of these data points, because we require 5 data points for a fifth-order curve fit, and I've entered them into the computer program. I just hit enter, and it will calculate 6 coefficients for the fifth-order polynomial. I can then take these coefficients and generate a graph to see how close they are to the actual data gathered in the field. Once we've got the coefficients, the customer can then take the water level recorder back out into the field with the data logger and record the voltages, and then bring the data logger back in and download the voltages into the computer and have it calculate out the water level in meters using the fifth-order polynomial, as long as the water level stays within the domain of the data we gathered to generate the coefficients.